What is electronegativity? It refers to the tendency of an element to become negatively charged or to become an anion. In order for an atom to become electronegative, it should be able to attract electrons to itself. In general, this would require a high effective nuclear charge, or ZEF, for that particular atom. In this video, we'll see the variation in electronegativity of elements, specifically across a period in the periodic table. There are two fundamental factors affecting the variation of electronegativity of all elements, that is, the effective nuclear charge and the atomic radii. Factor 1. Effective nuclear charge. The higher the number of protons, the higher its electronegativity. It is because the number of protons correlates with the effective nuclear charge. When there are many protons, the effective nuclear charge is also high, and thus, the stronger the nucleus attracts and hold another electrons into its outermost shell and become an electronegative atom. Factor 2. Atomic radii. The further the distance between the nucleus and valence electrons, the lower the electronegativity, and vice versa. When the atomic radii is small, it means that the nucleus is very close to the valence electrons, and the nucleus attraction force experienced by the valence electrons is significantly strong compared to the valence electrons of atoms with bigger atomic radii. In conclusion, another electron can be easily attracted into atoms of smaller atomic radii. We're about to dive deeper into the periodic table. But first, let's learn briefly about the earlier term effective nuclear charge, or ZEF, means. The effective nuclear charge, or ZEF, is the net positive charge experienced by the valence electrons, also defined with the formula Z minus the number of inner electrons. Now, looking into the variation in electronegativity of elements across a period, we should readily understand that all elements of the same period has the same amount of electron shells and consequently the same amount of inner electrons. Take for example the elements in period 2. They are all from different groups. They differ from their number of protons and their number of valence electrons. Going from left to right of a period, the electronegativity of elements increases. Why so? Going to the right of period 2, proton number increases. Thus, the effective nuclear charge of ZEF also increases. The higher the ZEF, the stronger its nucleus attraction to attract new electrons into its outermost shell. The higher ZEF also contributes to the smallest size atomic radii. Fluorine is known to be the most electronegative of all elements. But why so? Why not neon, since it is located at the most right of period 2? And why can't we say helium either? This is because both helium and neon are elements of group 18. They are noble gases. They are very stable due to having a stable octet arrangement for their valence electrons. They are stable enough that they don't need to add in another electron that would only bother the octet arrangement stability they have already achieved. Therefore, excluding the elements from group 18, fluorine is the most suitable element to be categorized as the most electronegative element. Let's compare between fluorine and lithium. Lithium, with the electronic configuration of 1s2, 2s1, has one unpaired electron in 2s orbital, which tends to be released to form stable duplet arrangement and form a fully filled 1s orbital. Thus, it's the least electronegative atom in the period 2. Fluorine, however, with the electronic configuration of 1s2, 2s2, and 2p5, has one unpaired electron in 2p orbital. So it tends to gain another one electron to form stable octet arrangement and form a fully filled 2p orbital. Thus, it is the most electronegative atom in period 2.